All right. So this is our last lecture on oxidation reduction. And so a couple quick notes for the whole class is tomorrow is Friday, and I'm going to be doing a review for exam 3. I just posted it, and so I'll record the review at this time at 1 o'clock tomorrow. And I know a bunch of people ask me, is the exam exactly the same? It's similar. And so I would recommend doing the review twice. And then the exam is Monday. So this is exam 3, and it's on thermodynamics and oxidation reduction. So use your weekend wisely, because next week we're done in a week from now. A week, some of you will be done in a week, and some of you will be a week in a day. So our exam 3 is on Monday, and it'll be same. So at noon, if you want to take it at noon, you'll come in. It'll probably be 2 hours, might be like a little bit over 2 hours, but you should be able to finish in 2 hours, and then like a 10-minute window to get it submitted. I have not fully decided if I'm going to have some multiple choice, just so you get practice again. It won't be as much as the first time. And then next week, after Monday, I'll be sending out an email with other stuff. So I know people are going to be sending me emails. The thing you want to focus on is this exam. A lot of the final is thermodynamics and oxidation reduction, and you want to do really well on this because this exam is worth the same amount as your final. So let's focus on that. Redo your study sets, and I'll talk more about tomorrow. The other big thing to worry about for next week is your demo. And so some people want to go Tuesday night, and then the others will be on Wednesday. And there's a couple people who still have not told me what they're going to be doing for the demo, so please make sure you do talk to me or email me, or I'll be emailing you. I think, yeah. So just kind of keep that in mind. Those are two big things for next week, which is the exam and then the demo. And I will let you know Sunday if I decide to do some multiple choice. It would just be a small part of the test, more again to give you some practice. It's not meant as a penalty, but to help you. So then when you have the final, it's not, but you all have had some practice. So I don't know that that's necessary. All right, our fairy card today is, by the way, make a wish. So you can make a wish. Maybe trees will grow out of our heads too. We are doing electrolysis. So those of you who were at yesterday's, Joseph talked about Humphrey Davies. And then there was also, I don't think anybody talked about Michael Faraday, but there's his picture. And so Humphrey Davy happened to be in the right place at the right time. That's just if I was going to do the Zoom on the other thing. And electrolysis is non-spontaneous. That would be the easiest way. So that's what it says here. It is a non-spontaneous reaction. So we have to force it to happen. So we're going to be comparing it to the electrochemical voltaic cell, which is battery. This one, electrolysis, you have to plug it in. You need to force the electrons to do something. Electrochemical is spontaneous, and so this would be a natural flow. Electrolysis allowed us to undo what nature did. So it is natural for the 1A's to become a +1. Why Humphrey Davies found so many elements was he was able to, with electricity, force the electron back into the 1A group. So he formed sodium solid and potassium solid and all those kinds of things. So he formed these all these elements that normally were found only as ions. And then a whole bunch of other folks who were around at the same time. All right, so we're going to draw this. Another big thing that's different, besides plugging in and the other one's a battery, is in electrolysis, you have one cell, whereas in the battery, you always have two cells. So if you remember the batteries we were drawing, it was always split into two, and so you had a flow between them of the electrons. In the electrolysis, it is one cell, and you do not split it. So you make one big cell. I can make mine a little bit lower. Here we go. All right, you're going to have electrodes. So something that is similar is you do have your 2 electrodes. You will have a wire that connects them. That wire then has to go to the wall and plug in. That's my image of the plug. That's our plugging into the wall. You can draw your own elaborate plug, but that wire is going to be plugging in. So the 2 electrodes, they're going to be the cathode and the anode. It doesn't matter to me which side you call the cathode and which side you call the anode. The cathode is always what? Any of you folks here remember? Or the anode, what is always happening at the anode?
Oxidation.
Is that which one?
Anode.
You got it, yes. Oxidation is always on at the anode, or Leo, and the Gur is always at the cathode. So that's what I was trying to be, my Leo and growling. So Gur means it's gaining the electrons. The electrons in the wire are always flowing to the cathode. That is the same for both. That the cathode is always gaining electrons, meaning the electrons in the wire. So this is where it's different. In the spontaneous one, it is a natural flow attraction to the cathode. In electrolysis, we're forcing the electrons when we plug it in, and so that makes the cathode negative. That is a big difference between them. Spontaneous versus non-spontaneous electrolysis. You got to plug it in. That's what non-spontaneous means. You have to force the electrons, and that forcing of the electrons changes the polarity. So the anode is positive in electrolysis. In batteries, the cathode is positive. All right, again, there's one cell, and the other thing we have to do, this makes 100% sense. We're making something happen that's going against nature. So you're starting always with electrolysis. You're going from the ions to the element, meaning a solid liquid. Well, I'll write the element. What I mean is you're always starting with the ion. So we're starting, the cathode is the cation. So the cathode is always the metal. So our example was SnCl2. That means at the cathode, I have the tin, and at the anode, I have the Cl negative. The names came from this experiment. So cations went to the cathode. That's why they called it the cathode and cations. I don't know which one came first. The anions go to the anode. All right, the tin is going to gain electrons, so I'm going to write it underneath. It gains electrons, and so it becomes tin solid. So we're forming something. This is how they actually can make a lot of the elements. And the chlorine is going to lose electrons, so the electrons would be on the product side here, and I'll make it, since the Cl2 is chlorine gas, when we go to the element, I'll add this up here, you're going to get a solid, liquid, or gas on the product side. So there's only a few that are gases. Those are the diatomics, like hydrogen gas, chlorine gas. If you make a gas, you do get bubbles. And if you really want to show, you can put your stick figure has passed out. Oh no. Probably not smiling. Because that's chlorine gas, and that's going to knock you out. That was actually the Fritz Haber, that was Jessica's talk. So use of chlorine gas was used in World War I. The thing that was really interesting from that, they ponder if that's what started the flu epidemic back then. That was in 1919, and that was right after all the chlorine gas was used in those wars. Something to ponder. So this electrode would actually probably accumulate the tin. So this is my tin there. And you can make the electrode as platinum. This one has to be platinum because chlorine is a gas. It can't be an electrode. Or you could use it as tin. You would not use copper or something like that. You would either have to use a non-reactive metal, or you could use something like tin and it would actually be accumulating more tin on it. So it's kind of a choice with that, and that's it. All right, with the battery, we have the 2 cells. Just a couple things that you can draw your 2 cells. Quick sketch. It's separated, the wire connects it. I'll make this the cathode and this the anode just to be consistent. So again, the cathode is gaining. That is the piece that is always the same. And so Alexander listened to me for the past few days. Cathode is always reduction. The anode, again, anode starts with an A, oxidized. Big difference. Cathode is positive. Anode is negative. The electrons are moving naturally, so they're attracted to the cathode this time. Here, they're forced to it. That's why it's negative. Does anybody see the other big difference that's going to happen besides this being spontaneous and the positive negative polarity? There's something I forgot. What are we missing?
The bridge.
Yeah, there has to be. There is no bridge in electrolysis. There's no bridge. And that's because it's 1 cell. In this one, you got to have a bridge. The anions will flow towards the anode. That's something else that is similar. So the anions are always, that's why it's called the anode, and that completes our circuit. And you would, of course, if it was a true electrochemical, you'll get to draw one in your homework. You draw one on your worksheet. If you have a lot of fun on your worksheet with your battery, you can earn a bonus point. So yeah, and again, for all of you who sent me your panicked or wrote a note to me, apparently there must have been some weird thing that happened last night at midnight because everybody was having problems with printers and scanners, and the number of you who wrote me notes. So know that you were not alone, and if that happens, send me a note like you did, or just try it again in a half hour and put a note and say, I was doing this. With the exam, I build in 15 extra minutes so that you get it in and you move on. All right, questions? So again, this is why those of you, when you did your famous chemist, or I'm sorry, when you did your element report back in 221, a lot of you kept having the same, like 3 people discovered everybody's elements because they were right when electrolysis was discovered. All right, there's a lot of words that come next, and it is, we want an aqueous solution. There is an issue, it comes with the chart. Oh, I don't have my chart. Sorry. And I usually ask you just with an aqueous, but water is here on the chart. And so if you were working with F negative, meaning we're going the other way, this time the F negative would be going to the fluorine, it would be the oxidation in electrolysis. It actually requires more energy than the water, and so you cannot make fluorine with this process unless you use liquid rather than aqueous. The same problem happens down at the bottom of the chart, and that's what those words are talking about. So I often ask as a liquid, but I'll show you when we get back. So here's the water, and so at the cathode, if you have an aqueous solution and any of these ions that are below the water were present, the water would be what gains the electrons because you have so much water there. It's 99.999% water. And so you can't actually make aluminum, magnesium, sodium, potassium, or lithium in an aqueous solution. They actually use molten. The word molten means, all right, whoops, that it's a liquid. So they took like sodium chloride, like from your salt shaker, and they heated it up till they made it into a liquid. You're not going to be able to do this at home. That's a demo that would not happen in your kitchen because the temperature you'd have to heat it to is much higher than your kitchen will probably go. But that's what those words mean. All right. And that's what this is talking about, that if the water is present, you would actually do, the water would gain the electrons. The reduction would happen to the water, the sodium would make. And so the difference here with the molten versus the aqueous is with the molten, that means that this is a liquid. There's no water present. It's an O. And aqueous means there is water present. So in the aqueous one, we would do the H2O plus the 2 electrons becoming the hydrogen gas. So you'd see bubbles and the hydroxide. The molten one means the sodium would gain the electron and form the sodium solid. All right. And by the way, this is what Humphrey Davy did. So Joseph talked about this actually beautifully yesterday. He actually built a battery out of 250 plates. Michael Faraday was his assistant. So as Joseph talked about, Humphrey Davy did a lot of experiments. He was pretty amazing. Really cool documentaries have been made about him. He did lectures and stuff for the public. But he ended up almost blinding himself and hurting his hands because he did a lot of crazy experiments. None of you do that with your demos. Be safe. Wear your goggles. Right. And so Michael Faraday, he hired him, and Michael Faraday was actually extremely intelligent, had no education. He was extremely poor, like had lived on the streets and became a bookbinder, and he just read. He became a bookbinder, and that's how he learned to read. And he read all of Humphrey Davy's stuff because he happened to be binding those books. And so he applied to work with him. And then he ends up coming up with our electricity and stuff. He could not even do algebra, let alone calculus. So he did not understand the math behind what he did. He just built it. And that was the quote I have at the bottom of your page that actually Joseph had in his talk, was that like a prince or somebody came and Michael Faraday, he asked Michael Faraday, what are you doing? And Michael Faraday's like, I'm busy with electromagnetism. And I think I'm onto something, which is why we have electricity. Oh, that's what he said. Sorry, Joseph had a different quote. I thought I put a different one on yours. Was when the king came, he said, I'm not sure what I have, but you're going to figure out how to tax it, which of course they did. There was actually a gentleman in this country, in the United States. This is when the Revolutionary War is about to happen. And he actually figured out electricity also. He had an education, he understood it. However, we were a colony at the time. The communication between here and there is weeks and weeks, and nobody was going to listen to a little colonial guy. And so nobody knows Michael Bolton, but unless you know the story. All right. He actually, at one point, one of them traveled. Either Michael Faraday came here, or after the Revolutionary War, or Michael Bolton went there. The two of them got together, and Michael Bolton actually had to explain to Michael Faraday what all was going on, which is pretty cool. All right, we're going to do some calculations now, and we're going to do factor labels. So those of you who are with me, you're back to what we did in 221, and those of you who had Bernadette, you're going to love this too, because I know she does a really good job with factor label. And like Catherine, you had Dr. Russell, so just follow along. You're going to love factor label too. Dr. Russell is not a fan of factor label. Joey's giggling in the background because he's going to take him. All right, we are going to, this piece here is a Faraday, which we talked about yesterday. You can write your F however you want, but a Faraday is equal to 96,500 coulombs per mole of electron. And those of you who are comfortable with factor label dimensional analysis, you can see this is a factor that we can flip it however we need to. A coulomb is a charge. It's a true rate of charge. All right, the other pieces we have here are amps. And an amp is the flow of charge. I was explaining it not quite perfect the other day. So if you're thinking of water flowing, that would be here, it's electrons flowing, like through your wires and stuff. And so that's what an amp is a measurement of the rate or the flow of charge per second. So like here, and we see this 10 amps, that means 10 coulombs per second. So we're going to see that as a conversion factor when we do this. And then a volt, we've talked about when we did our math the other day. A volt was a joule per coulomb. So that's the force, what's moving it. And then a watt, kilowatt hours is how, if you look at your electricity bill, it's in kilowatt hours. And so a watt is a joule per second. So when you do this in physics, you learn it as amps times volts equal watts. And you do it algebraically. We're going to do it factor label because we're going to use your periodic table. So always good to have a periodic table around. All right. We're going to start, if time is given, you start with time. If mass is given, you're going to start with mass. You start with the thing that has one unit. The amps or the volts or Faradays, those are conversions. All right, so we're going to start way over here with 1 hour. And the way I teach it is I just make what are called railroad tracks, but you can do parentheses. There is nothing down here, so you can draw whatever you want. You can draw a gnome, you can draw a heart because it's the easiest thing to draw. These are in seconds, so we want to change our hours to seconds. So you can do 60 minutes per hour, or you can just go straight to seconds, 3,600 seconds to 1 hour. The whole thing is for the units to cancel, right? So the hour was here, so we do, you guys know that. I'm going to bring my amp in next. So I'd say that there's 10.0 coulombs per 1 second. So my seconds cancel, and I'm at coulombs. This Faraday's constant, he did not call it after himself. It is named in honor of him and his brilliance. And again, it was probably because he was not educated. He was completely self-educated, that he thought so far outside of the box. So I'd wonder what he'd think of our cute little boxes that we get to be in on Zoom all the time. All right, coulombs cancel. I'm sorry, that should say moles of electrons on top. There we go. It wouldn't be me. It would not have recognized me if I didn't make a mistake. All right. So we're at mole of electron. That's where our periodic table comes in handy. And I have a whole drawer full of them. We're talking about aluminum. So there are 3 moles of electrons per every 1 mole of aluminum. Where am I getting the 3 from? Oh, what charge does aluminum like to be? So it's not the total number of electrons. This is the charge. So like up above, if we were, this is the question you would ask me, Alexander, yesterday, like where was I getting the electrons from? So the example up above, it would have been 2 electrons. For this example, because it's aluminum, if we were doing sodium, it would be a +1 because sodium is a +1. All right, and then we go to grams. 1 mole, there's no answers. Somebody's gonna have to punch this in. And you can do 27 or 26.98 grams of aluminum, and we punch it in. And questions on that setup? I can't believe I didn't give you answers. I had 3.36. So Megan, check my answer. I'll give Alexander his other bonus point. All right. So, questions. All right, we're going to do the next one. We're going to start with the 1,000 kilograms, and we got to go to grams. So 1 kilogram is 1,000 grams. And again, you can use parentheses. I honestly have no idea what Bernadette does. It was a student who taught me to do the railroad tracks. It's the guy, whoever teaches at Sandy High School. And this was like a game changer like 12 years ago. All right. I'm looking forward to the fall when I get to teach brand new students in 151 how to do factor label in this format. It's going to be fascinating. I just keeping that word fascinating in mind because It doesn't have a positive or negative connotation to it, right? So you just go, it's fascinating. It will be whatever it is. We're doing aluminum again. And again, these guys, when you're running electricity, it's the aluminum that is in the wire that we're making aluminum. So the thing that's fascinating about this question, so 26.98 grams this time will be in the denominator. You don't want to just say grams. You want to tell me that we're dealing with aluminum. It is aluminum because it told you there it was aluminum. And for every 1 mole of aluminum, again, it's in the +3 state. We have 3 moles of electrons. Once you get to your moles of electrons, Faraday's constant comes in. So this time, the mole of electron is on the bottom, and then 96,500 coulombs is on top. Right, you have this is the new piece. For those of you who've done factor label, that's our new piece, is the mole to mole ratio is to moles of electrons. We get to coulombs. We're trying to find kilowatt hours. So before I go on, a kilowatt hour means K for kilo. It means a watt, which is a joule per second. So it's a kilojoule per second. That would be a kilowatt, but the kilowatt hour, it's not a kilowatt per hour. So it's a very strange unit. It's kilojoules times hours per second is what a kilowatt hour is. I know nobody ever thinks about that when they get their energy bill, but that's what it is. So we're at coulombs. What we know is the EMF, which is the electromotive force. That's the voltage of your battery or whatever you're running through. So a volt is a joule per coulomb. So this would be 4.50 joules per coulomb. So our coulombs would cancel. That gets us to joules. So if we cross out all our pieces, I have the joule, which is my piece there. Now, if I had been paying attention, well, we're going to change it to kilojoules, so 1,000 joules to 1 kilojoule. There is actually a trick where you would not have to do that step. And if you're playing for a bonus point, you can tell me what I could have done different so I could have avoided this step. But I need to be in kilojoules, so now I'm in kilojoules. And this last step is a weird step. I don't ask one of these in the homework. I have it on this because this is a really interesting question. 1 hour is 3,600 seconds. The hours nor the seconds cancel out. We bring in a factor where we need both those units. It's a really bizarre thing, but it works great in factor label. So I end up with kilojoules times hours per second, and the answer comes out huge. It comes out as 1.3 e to the 4th kilowatt hours. And I don't really look at my electric bill that much, but that's a huge number. That's like an outrageously huge number. And so for any of you who don't know this, this is why Bonneville Dam and John Day Dam and the Dalles Dam were built. They were built specifically because there's a lot of bauxite in this area and we needed the aluminum. So has anybody ever been to the Washington Monument in Washington, D.C.? It was actually made, the top of it actually has aluminum, not gold. It actually has aluminum. Aluminum used to be more precious, more valuable than gold. And that was because we did not have a way to make aluminum. And then somebody talked about in their presentation, I'm trying to remember who, but I think was it you, Natasha? Was it Le Chatelier's dad had figured was one of the people? Yeah. Who figured out this process of running electricity. And again, it was being in the right place at the right time and realizing we could suddenly, from the bauxite, put the electrons back in the aluminum. So for thousands of years, nobody had aluminum. Aluminum is not in the Bible. So the 7 metals that are in the, 5 metals that are in the Bible are ones that are really easy to turn them back into their state without having to do this whole thing. You could just warm them up like gold, silver, and copper, and lead and tin. So the ancient metals. Anyway, so the dams were built because we needed aluminum to make airplanes. So there was a great war going on. This is in the 30s. And one of the reasons that the US and the Allies won the war was in the US, even though we were not in the war yet, this is in the 30s, they had the foresight to build dams in the 20s and 30s so that we could start making aluminum. And we were able to keep making planes for Britain. And so as British planes got shot down, we were able to replace them. That was a problem that Germany was not able to make enough aluminum to keep replacing their planes. So when everybody curses the dams with the salmon and stuff, you are not in a fascist country right now, although it might feel like it some days recently. But anyway, it's a really cool question. It's also why when there's an energy shortage, they actually shut down the aluminum plant because they're using all of our electricity. So you and I still have electricity, but they just, and it's also why we get a dime back now, I think, if you return aluminum cans. So it's why it's actually cheaper for them to reuse the aluminum that's already got the electrons than to try to make new aluminum. Again, they're not making them from scratch. All they're trying to do is get those 3 electrons. This is a really pricey process to do. All right, let's do the last one. The last one says, how long is it going to take? We're going to work with zinc. And so there's where I want to start. This is 2.5 grams. So again, if you have a mass, start there. If you don't have a mass, then you're starting with time. So 2.5 grams of zinc. All right, when you do these, you would look up on your periodic table, you would find zinc, because we're in chemistry, so you're going to go to moles. So, and for those of you who are like, I went to University of Oregon, I'm not very good at factor label, that's great, that's an excuse. You're now in my class at Mount Hood Community College. These questions you have to set up in one setup. And so, yeah, I don't care who you had, you can do this. This is awesome to be able to do this. It flows. Yeah, and those of you who, you probably resisted Bernadette when you first were learning this, and you were like, I don't like it, but it's awesome once you learn it. All right, zinc is 65.39 grams to 1 mole of zinc. And so the grams cancel, we keep going. For every 1 mole of zinc, we're dealing with electricity, electrons, redox. It's all about the electrons. We're going to the charge of zinc. Zinc likes to be a 2 charge. So conversation I had with Alexander yesterday after class, if you're in doubt, go with 2 electrons. It's not always 2. 2 is like 90% of the time. The transition metals like to be a 2. The exception is silver. If you have your periodic table, silver, copper, and gold are called the 1As because they actually like to be, in the case of copper, I'm sorry, silver likes to be a 1, gold actually likes to be a 3, copper likes to be a 2. It's a dysfunctional family. But anyway, zinc likes to be a 2, that's why it's called a 2B. And then we do Faraday's constant because that gets us to coulombs. So again, your test is timed, your final is timed. You guys can do this. You can make a note card, but you want it organized. If you don't do the work, if you don't do your own homework set and then do it again and feel comfortable with this, it's not going to be comfortable on the test. See the test as a game. It's a game to see if you really are ready to go to the next level. And you all are. You're all capable of this. And we're coulombs. I have amps. Amps tell us to seconds. So the 2.12 stays with the coulombs and the 1 second would go up on the numerator. So this time I had to flip it for my units to cancel and I had to find my question. All right, if you punch it in here, you will get 3,480 seconds. you'll lose a little bit of credit. My question doesn't say how many seconds, it says how long. Now, if somebody asked me, how long is class going to be today, Dr. Sherpa? And I said 3,480 seconds, you would all give me that look that these beautiful people are right now. This is like, what's that mean? Well, it means it's a little less than an hour. So always then, once you get to seconds, you're going to have to probably make one more step and change it to something reasonable. I would go to minutes, because saying 0.96 hours would also be a weird answer. So you could do it up here. You could add your step up here, 60 seconds to 1 minute. And you would punch it in. And now our answer, I did it earlier, is 58 minutes. So if somebody said, how long is class going to be today? And I said 58 minutes, they would go, okay, they got that. But again, like 0.96 hours, you're like thinking that person's like really unusual. All right, we got one more page. Go ahead, Natasha.
Can you explain why when we went from Faraday to the amps, why it went to 1 second and 2.12 coulombs?
This is
How that works, that ratio?
This is specific to this question. That's this, the 2.12. And it's what amps mean. Amps, again, mean coulombs per second. So what this 2.12 means is you have 2.12 coulombs per second. But for the unit to cancel, the 2.12 had to move to the denominator. So I'm basically dividing by the amps.
Okay, so whatever the charge of the amp is, that becomes the number of coulombs.
That is the coulombs, yes.
Okay.
And it's always per 1 second. So really good question. It's like molarity. Whatever the molarity is, that's your moles per 1 liter. It's the same idea here. Or like with periodic table, that is your grams per 1 mole. So the number with the amps is your coulombs per 1 second. Yeah, or with voltage, that is your joules per 1 coulomb.
Okay,
yeah.
Thank you.
All right, that's electrolysis. The biggest thing with electrolysis, you can go back to the top of the page, it is the most missed thing on the midterm, is the half reactions. The cathode is going to be the cation, and the cathode means you're gaining. You're always ions back to the element. We are undoing what Mother Nature did with electrolysis. It is not natural. It's non-spontaneous. We're pushing against nature, whereas the battery is a spontaneous movement. All right, and so here we're making the chlorine gas, for better or for worse. All right, last page is practice. This is all the electrochemical stuff that we're going to be doing. So I'm going to pause the video because I want to give you guys like 10, well, yeah, try it. If you don't like balancing, just move to the bottom, but the top one is splitting. And on number 2, you're going to need your chart and figure out how it works. So I'm going to pause so these folks can try it. All right, we're back. You didn't even know we were gone. Before I forget, I wore this shirt the other day and I forgot to show it. So that could be the thing that people have to email me. But I made these in Nepal. They're back. Is he backwards or is he forward? So it says, yeah, they have all these shirts there that say Yak Yak Yeti. And I got the guy to make one that said Yak Yak Redox. So the last yak is a redox. And so I always wear it when I'm teaching redox. And so if you go to Nepal or to a country where they make the shirts with the little sewing machine, you can make your own redox to wear and be super geeky. All right, we're going to balance the equation. So we split it into 2 half reactions. Let's do purple. And I know you can do that step. Everybody can. And I'm going to run out of space. All right. So balance the elements other than the oxygens and the hydrogen. So be careful on this one. Did you remember you're going to need to put a 2? in front of the hypochlorite because there's 2 chlorines. So if you forgot that, none of us will know because you're watching this on a video. All right, I'm going to do my chromium one. The chromium is balanced. I have 3 oxygens to 4. So I need to add my water over here. That means I need to add 2 hydrogens to my other side. So I have 4 oxygens. Oh, I'm sorry. I have to add 5 hydrogens. So there's 3 here plus 2 more. Treat it as if it's acidic. And then the very last step is to go basic. There are ways you can not do that, but it doesn't turn out well for many students. All right, we have to do the electrons. So it shouldn't be too bad. My reactant side is neutral. My product side, I have a -2 and a +5, so I have a net +3. So I need 3 electrons on this side. Right? All right. So is that Leo or Gur? Are we oxidizing or losing? Oh, we are losing, which is oxidation. I said that well. So this is Leo. So when I ask down here, I can actually answer all of this right now. This is the reduced one must be the chlorine. And so when you're asked what's oxidized reduced, it's going to be one element. And the reducing agent would be our Leo, the reactant side, and it is not going to be the water or the hydrogens or hydroxides anytime you have another choice. I want to take a moment to do the CrO4 because it was a question a couple people had in my office hour today. And sorry about that when I move up to that light. So CrO4 2 negative, the question was about doing oxidation number. This shows up on the lab, the QA3 lab. The question had to do with that -2. That was when you do oxidation number, when you add up all the oxidation numbers, instead of going to 0, you go to -2. This is to remind your brain. You might see like one question on the final with this. And so this is, again, a subtle review. The oxygen is a -2. Every oxygen is a -2, and there's 4 of them. That gives us a -8. That would make the chromium a +6. So the chromium +6 -8 gives us the net -2. So that 2 negative is the overall, it's not just the oxygen. The chromium here started out at a +3 and it's ending up at a +6. So that's what Leo is. And so when we used to do this back in 221, we'd look at oxidation numbers. Now we can just look at the half reaction, and it's actually a lot easier. All right, our second reaction, our second half reaction, we have the 2 chlorines. Make sure you get those first. That means I'm going to need 2 H2Os on my product side and 4 hydrogens on my reactant side. Then my electrons do need to go on my reactant side. This is a +4 and then a -2, so we're going to have 2 electrons. The electrons need to be on opposite sides because whatever one you have a Leo and the other one's the Gur, and it definitely is. The chlorine was gaining. The chlorine here is a +3 because the oxygen's I'm sorry, it's a +1. That was good math. Chlorine's a +1 going to a 0. So it's going through reduction. All right, this is a question. The electrons have to be the same. So the top equation, my chromium equation, we multiply by 2. My chloride, we multiply by 3. Actually go through and do it. Using color can be really helpful. So you have a 2, a 2, 2, and then this becomes 10, and this becomes 6. So 2 waters, 2 chromium hydroxides, gives us 2 chromates and 10 hydrogens. All right, this becomes 6, 12, because we're multiplying by 3s. 6, 3, and 6. All right, now we cross out. So I'll use green. the electrons must cancel. Now, both equations have waters and hydrogens, so we're going to reduce them. We can cross out 10 of the hydrogens from each equation because they're on opposite sides. If they were on the same side, you would just bring them all down. This becomes just 2 hydrogens. And then we can do the same with the water. These 2 waters will cross out, and now we're down from 6 to just 4. And then we pull it all down to our next step. So we have 2 hydrogen ions. Actually, I'm going to run out of space. You can pull it all down and neutralize, or you can neutralize at this point. Do you guys have a preference? Do you want to pull it down and neutralize? Okay. So we'll do 2 hydrogens. Put a line. 2 CrOH3 and 6 hypochlorites. 2 CrO4s with the 2 negatives, so make sure the students who have trouble with this, it's because they get sloppy with the charges or they just don't practice. You just have to go back. We've had several in here. There's the first page of your study set is 4 of these. So actually do them, and then when you check the answer, you're just looking at the final answer. You actually will know you have it right when you do the checking. This is basic. I will always tell you if it's acidic or basic. So treat them both as acidic, and now we have an extra step. So what is our extra step? We're going to add hydroxides. The key is you have to add them to both sides because we were balanced and now we're suddenly adding something. So the hydroxides, the number of hydroxides is the same as the hydrogens. So you have to, in this case, add 2 hydroxides to each side. These do not cross out. It's not the same as the electrons or the hydrogens cross out hydrogens. These guys form 2 waters. So we now have 2 H2Os on this side. Oh, but before I bring it all down, there are H2Os on the other side. And there were 4 of them. So these 2 H2Os that I just made, they're going to cross out. And these 4 are now going to become 2. And yeah, I didn't give you enough space probably. So I'm going to squeeze it in down here below. So 2 CrOH3s, 6 ClO negatives. And we're going to hope it's balanced. 2 CrO4, 2 negative. If not, I have a huge board below me. So 3 chlorines, 2 waters. This is actually a really good one because it's a pretty tough one. 2 OH negative. I just randomly picked one. I didn't know it had all these steps. So it's really good if you can do this one, if we got it right. All right. So we're going to check the oxygens. I have 3 times 2, so I have 6. And then I have 6 more. So I have 12 oxygens on the side, right? So 6 and 6. So over here I have 8 plus 2 plus 2. Oh, good. I have 12. It's always a surprise to me. It will be like when you do it also. All right. So the charge is our next piece. So on my reaction side, it's simple. I just have 6 negatives. So I have a negative 6. And we're going to hope for the best over here. I have 2 times negative 2. It's negative 4. Neutral, neutral, and a negative 2. So negative 4 plus negative 2, and I did it right. Hooray! High five. Virtual high five for everyone who got it. And everybody's going to go back and do it. So questions. All right. So question number 2 is worded funky, but you're going to see this wording again. So the key is this word here. Electrochemical means we want it to be spontaneous. It's going to work. And so you need the chart. So it's zinc and silver are the two pieces. So we did one like this the other day. Here's my silver is way up here. And I think my zinc is way down here. All right. The one, if I ask you to write the equation to make it electrochemical, you're making it spontaneous, the lower one flips. So you keep the higher one. So the silver is going to be silver ion plus the electron. So let's go ahead and write that. So, you know, I'm under a lot of pressure. I don't know if anybody else noticed this, but the last two videos were exactly the same length of time, which I think is like virtually impossible. And I thought I had uploaded the wrong video, but to have two videos exactly, they're both an hour and 19 minutes and like 2 seconds or 1 second. So I don't think that's going to happen today. All right, what was the silver? Was 0.8 positive. All right, and now we take the zinc, and the trick with the zinc is we flip it. So it's going to be the zinc solid. So the first one's my gaining, my GER. My second one's my LEO. So the zinc is the one that got flipped. It's now losing electrons. And when we flip the equation, it's just like what we do with delta G's and delta H's and delta S's. You flip the equation, you just change the sign. So now it's a positive 0.763 volts. And then our net equation, because I did ask for a net equation. Any questions on the chart before I do my net equation? I didn't give myself enough room, but we'll squeeze it in. For our electrons have to cancel. Don't forget to do that. So I have to multiply my silvers by 2 so that my electrons cancel. So we will end up with 2 silver ions plus the zinc solid goes to the 2 silver solids. Again, the order doesn't matter, but the charges and what's on the left and right does. C, we already did up here. We add those, we get 1.563 volts. I don't know why. Oh, I think I just did everything with 3 sig figs. But this is in the black is my overall equation. And then I asked, which is the anode? This is back to the question I asked earlier. Leo, because of the O in Leo, is always the anode. So the zinc solid is my anode. And then the silver, so the zinc is the anode. It can be nice to write that in. The silver is the cathode. It's true if it's electrolysis or electrochemical. The cathode is always gaining electrons. This is electrochemicals. My cathode is positive. So the silver is the positive. It is not called a charge. It is called polarity. These notes are because at the bottom we're going to make a battery. All right, the standard cell potential was just the chart, and we already figured that out. We can go through the next steps, kind of just to remind you the formulas you're going to use. Free energy does not mean we're in a communist state and everything's free, or is it? Except your like civil liberties are not free. This is this formula, delta G equals negative NFE. The E is from the chart. I put them in the right order for this page as opposed to yesterday. And this is the question. The N is the electrons, and it is almost always 2, but it is not always 2. So just be careful of that. It is the number of electrons that cancel. So if we had done this with the original equation at the top of the page, it would have been 6 electrons because that was our number that canceled. but we're doing it with the silver zinc. So we have -2 electrons. You can just write F or 96,500 joules per electron, coulombs. Sorry, coulombs per electron. And then E is this. And the units of volts are joules per coulomb. I like to go to kilojoules because delta G's are always big numbers. So then I always divide by the 1,000 joules to 1 kilojoule. And you should get in the ballpark of my number around -300 kilojoules. Right. Equilibrium constant is, we're just going to use the same one we used when we did your free energy homework set. Delta G equals -RT natural log of K. So several of you on your worksheets did this wrong. You forgot that natural log. Whenever you work with K's, there's an exponent. There's going to be a function. So we rearrange. You're going to have delta G divided by the RT, -RT, but it's e to the power of that. So a lot of you on the worksheet were just doing delta G divided by RT. The other thing, several people were in my office hours last night and we're struggling with this because people struggle with this every year. You know, don't be shy. Just come to my office hours. It's not a big deal. I will be there tomorrow, Friday. And I'm willing to do Sunday evening since you guys have a test on Monday. So if you send me an email Sunday saying, yeah, I do have questions, can you open the Zoom? It will be the same. It will be the Sunday 6 p.m. It's the same link. All right, delta G was our -301. I wanted to go through this because this is a question several people had. Over negative, there is a negative. My two negatives cancel. Your answer needs to make sense. So if it's not, it's that you lost the negative. The other thing to be careful of is your R. I do it in kilojoules because I like not having the huge number with all the zeros. So 0.008314. Or if you prefer 8.314 e to -3, and that's kilojoules per mole K. And the temperature, if you're not told, is 298 Kelvin. Again, standard temperature is 25 degrees. That's a really warm day. That's like what's going to be here in another hour, about 85 degrees. They are changing that number, but for our purposes, it is this. Gas laws is the exception, and you would punch this whole thing in and we get this number. And then the question is not on mine. You would be asked at this point if your answer makes sense. G is a different question. My answer makes sense. E is positive. Delta G is negative. So E's and delta G's, this midterm, can be positive or negative. Negative delta G means we're moving forward. Positive E means we're moving forward. They're technically little not signs. That's why we can find K. K is not positive or negative. K has a positive or negative exponent. It's different, so be careful with that. My K is definitely greater than 1. It's huge. 52, e to the 52. That means it is pretty much a one-way reaction. This thing is going. We're going to make silver solid. This is actually really cool. You can take a piece of zinc and put it into silver nitrate. Those of you who had 221 on campus, remember the titration? We made a whole bunch of silver nitrate waste. I've had, oh, I shouldn't be recording this, but I've given people those buckets who have zinc or copper at home, and they will actually make silver by putting a piece of zinc or copper in the bucket. They make a whole bunch of silver, and then they take it into the silversmith, and we'll get a couple $100 and pay for the class. And so, and they have ways to get rid of the waste in the proper way then. But don't tell Ashley's, don't listen to this and tell the people you used to work for. They'd be horrified. I think it's awesome. All right. So yesterday my layout wasn't perfect. You would be doing this and ask if it makes sense. These all go together. That was like the worksheet 5. You had a question. It didn't have the E's yet. Then this is a different question. We're going to go non-standard. We suddenly have something that's different. So before we solve F, before I solve F, I'm going to actually answer G because I have that much confidence in myself because I did so well at this yesterday. The the zinc ion is a piece that is not standard. Standard is 1 molar. So if the zinc is 0.1, the zinc ion is on the product side. So if I decrease the zinc ion, which is a product, it's going to shift forward. This is all I need for the explanation. We move forward. So if it moves forward, what should happen to the cell potential? It's going to go up. This is great. All right. Oh, and if we do our math right, it does go up. So we start at 1.56 and we're going to end up at 1.59. So you won't make this mistake. So on the midterm, rather than having your notes that you're flipping through, you're going to run out of time. Go through your notes, do them again. So you do the midterm as if you're doing it in class. Yeah. All right. So we have E equals, this is the Nernst equation, Catherine, that you talked about. E equals delta, E naught minus 0.0257 over N. N is again the 2 electrons for this one, times the natural log of Q. Q is products over reactants. So these numbers up here that we calculated, the delta G and K, they don't go with this. We ignore the solid, so it's just the zinc ion over the silver. Be careful because the silver is squared, so that would be our formula. The silver would just be a 1, we'd plug in. This E is the one we found up there. The N is 2, and you punch in, and you should get my answer. So you would show, I scrunched this all onto one page. So if this was like on the midterm, this would be spread out over 2 pages, so you would have a lot more room. And you're going to get draw a battery. We're going to draw one more battery. I can do it down here. Should use green since, there we go. So you make 2 compartments. You can separate them as much as you want so you can have fun making your bridge. Right? One of them, so the electrodes, this is actually good because your electrodes are not platinum this time. You have metals in the question. One of them is the silver and one of them is the zinc. So this is silver and this is zinc. And then, before I go on, we actually labeled everything up above. My silver is my cathode, my zinc is my anode. So I'm going to go with that. So this is my cathode. Oh. My anode. So cats have paws. That works for this because it's spontaneous. All right. This is negative. You have to have a wire to connect them. And the electrons. Anode means losing electrons because it's Leo. So the electrons are going the other way. So you have to show me the electrons. And you would not get full credit. What am I missing? I complete the circuit. It's where you're going to have fun. You can do that if you want. And the anions flow this way, or you can make your bridge. Let's see if we can make a beautiful arched bridge today. If you want the anions move towards the anode, if you're really good, you can draw a cat. The cat has to move towards the cathode. He can't stop and meditate. Have a big tail. I'm not the best artist. It's a stick cat. He's walking. The cat has to walk towards the cathode. All right. I was supposed to be a lion, not a cat today. Did a little better than last time. Questions? All right. I'm going to stop.